So the plan for today is to look at propositional logic, primarily with semantics. So we already had a session looking at the syntax, so today we're going to be focusing on the semantics. Just a quick recap on the difference between syntax and semantics. Syntax describes how we can form the sequences of symbols. So, for example, with propositional logic, we'd say a statement can be something like an atomic, or P and P, or P or P, or P implies P, or not P. I think that's all of them. But yeah, this would be the syntax, but we're not going to be looking at the syntax today. We're going to be looking at the semantics, and the semantics is about assigning actual meaning to those symbols. What do those symbols actually mean? So yeah, let's get started. We're going to start with this. So we have true and false. These two symbols just represent true, that's true, and an upside down T like this represents false. If you guys wanted to know the LaTeX equivalent, it's /top and /bot. I think this is called a tack, I'm not sure, but yeah, so whenever you see these throughout today's session, that just means true and false. Okay, say hi to phi, guys. Phi is a magical symbol. We're going to see exactly what it does, and I know Hux will probably be covering this as well when we look at semantics of predicate logic. But phi is a beautiful thing. So what phi does is it takes an atomic input and it returns true or false. It evaluates that input. A truth assignment, the definition of a truth assignment is just something that assigns truth values for each atomic proposition. The truth values are just this. T and upside down T, true and false. And so given two atomic propositions, let's say we had P and Q, and we had a formula P or Q, then one possible truth assignment for the values P and Q is phi of P is true, and phi of, that should be Q, and phi of Q is false. So let's say P is true and Q is false. If we had something like a trace table, and we had, a truth table, and we had P, Q, and then P or Q, whatever here. So this could be 0, 0, 0, 1, 1, 0, 1, 1. I mean, these would actually be T and F, but these are the truth assignments. It's this column here that says what the possible combinations of values are for P and Q. But yeah, so all phi is it's a way of evaluating an atomic input, and it returns true or it returns false. T and F representing true and false here. One thing, you might have seen me use this as true and false, and you might have seen me use the words true and false, and you might see me use the words T and F. So T and F is used in maths, whereas these two are used in logic. So phi will convert anything we do in logic into a mathematical expression. So we're going to be using these whenever we're talking about the mathematical representation of different logical expressions. So, moving on, the extended valuation function just defines some extra stuff. So instead of, as well as atomic inputs, if we evaluate the logical true, so that's this, we just get T for true. If we evaluate the logical false, which is this, we get F, which just represents false. And then phi A or B is true if either phi of A is true or phi of B is true. Phi A and B is true if phi A is true and phi B is true. So these are quite trivial and quite simple to understand. Phi of A implies B is true if phi of B is true whenever phi of A is true, and phi of not A is true if phi of A is false. So the idea is we can create these larger extended valuation functions, and they just break down into these smaller parts, and we can easily evaluate these because they're just a single thing and we want to know whether it's true or false. So we're going to use these to sort of turn a large logical expression, break it down, decompose it into these smaller chunks of atomic phi functions, and then that can be used to then deduce whether something's true or false. So yeah, with the extended valuation function, we can mathematically deduce the truth value of a logical formula. So it converts logical to mathematical with regards to a given valuation of its atoms, which is just a possible combination of values for the different atomic inputs. So before we try and see that in practice, I just wanted to go over a few terms. Okay, so if phi of A is true, we can say phi satisfies A. This is just some terminology you'll see. And A, so A is satisfiable if there exists a valuation, just a single valuation needs to exist at least, phi, such that phi of A is true. So it's satisfiable if at least one valuation leads to A being evaluated as true. I just wanted to go over these four terms. So what could someone drop a definition of satisfiable in the chat, or if they want to come up, feel free to request to speak. So, I see two of you are typing. I'll wait for. There exists. Good. Okay, so satisfiable. There exists some evaluation which results in the formula being true. Yeah. Okay. And so, what about unsatisfiable? Because I know sometimes you might get these two confused, unsatisfiable and falsifiable. So, what does unsatisfiable mean? There is no possible, there's no possible valuation. So what is falsifiable in that case? So yeah, good. That's unsatisfiable. What about falsifiable? There exists, so there exists some evaluation which is just identical to satisfiable, but instead of true, it's false. That results in the formula being false. And finally, what makes a formula valid? Yeah, all possible valuations result in the formula being true. So, it's just a good thing to keep in mind the differences between these four terms. But yeah, I see that we've all sort of got that understanding. If there's no questions there, we'll move on. If you do have any questions throughout, just drop them in the chat. Okay, two other terms, soundness and completeness. Now, we didn't go over these in a lot of detail in the lectures. I think it was just kind of sprung on us in one of the last few lectures. But this is, if it's unsatisfiable, it's also falsifiable. So if it's unsatisfiable, then, yeah, this would imply that. And this would imply that, I believe. Yeah, cool. Yeah, okay. So, soundness and completeness. So soundness, every provable formula is valid. And completeness, every valid formula is provable. So all this means is, if we have something like A, and we reach something like B, and this is just a bunch of natural deduction, let's say. If A implies B is provable, then soundness tells, by soundness, this is also valid. And similarly, if every valid formula is provable, if you have something like A implies B, then that means there will always be a way to prove it. That's all these two terms mean. And it's quite trivial and simple, I guess, but because whenever we're making a proof, it's just us proving that something is always true, no matter what the valuations are. So whether A is false or whether A is true, in either of these, this would always hold. It will always be both provable and satisfiable. Wait, no, sorry, both provable and valid. Yeah. So yeah, that's just something that we kind of implicitly think about. Okay, I wanted to try a few questions. Let's start with something like A implies B and C. Or let's do A implies B or A. Okay, so let's say we had something like this. If we drew out a sort of parse tree for this, it would look something like this. So what we want to do is we want to focus on the first, well, we want to break it down into these smaller chunks, because we know phi can only take in one thing. So let's say we have something like phi of A implies B or A. What we want to start by doing is we want to split this up into if phi B or A whenever, so this is just using the rules from earlier, whenever phi A. So if phi B or A whenever phi A, then we know this is true. And we know this is true if phi, so if you go back to our or, if either this or this. So if either phi B or phi A whenever phi A. So from this we can gather this whole phi expression is true if either phi B or phi A whenever phi A. So then let's say we had a truth assignment of, I'll do this in blue actually, let's say we had a truth assignment of A equals true and B equals false. Okay, so substituting that in, this kind of gets converted to phi B, so we're just evaluating B. So this would just turn into false. Or phi A, we're just evaluating A, which just turns into true. Whenever phi A, whenever true. Okay, so false or true whenever true. False or true just simplifies to true. So if true, when true. And this is simply how we can prove that something's valid, because we know true implies true, and so this is the mathematical way of proving that. We've converted this logical expression, instead of using the steps of natural deduction, we've converted this into this logical expression into a phi function, and then we've used these rules sort of recursively until we get down to these base cases, which is a single atomic proposition inside phi. And as soon as we reach that, we can sub in our truth assignment into those phi functions, wherever we see it, and then we can evaluate that mathematically. Does that make sense? So, out of these three, we know it's satisfiable, and we know it's valid. So, from that, we can gather it's provable by what? Soundness or completeness? If we can gather it's provable, given it's valid, what are we using there? Soundness or completeness? Completeness. Good. So, because we know it's valid, we can then assume it's provable. So going this way would be completeness, and going this way would be soundness. Good job. Okay. Let's have a go at another one. Let's try and convert it all down into these atomic propositions inside phi, and then see what we can do. To see if it's valid, do we not need to check all possible valuations? So what this actually does is, yeah, so to check if this would be valid, I think you're correct. We'd need to check false, 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 true, true, false, and true, true. Yeah, so what this step does is this just converts it into maths. And then you'd have to trace this through with like all of the possible valuations, all of the possible truth assignments. But we can plug that into this new mathematical expression, and then we can gather from that it's valid and that it's provable. Yeah. Okay, let's have a go at this one. So let's say we've got this. We start with phi A implies B and A, or A or not B. And we want to evaluate this in the same way we did the other one. We want to take some steps. I'm just going to take a screenshot of this and send it in the chat so you guys have this on hand. Does anyone want to talk me through it, or or come up on stage and have a go at breaking this one down? Sorry, what does... Okay, so all phi means, this is called phi. Phi just takes an atomic input and it returns true or false. So phi of p is true and phi of q is false. Say we wanted p to be true and q to be false. It just takes in this input and it evaluates it, tells us whether it's true or false. So we can sort of put things, logical expressions inside phi, and it converts it into a mathematical true or false. Yeah. Does anyone want to come up on stage and have a go at this? If not, I'm happy to talk us through it. I'll say 20 seconds. If no one says anything, I'll talk us through it. Okay. Right. Okay, so where we started here is we looked at this and saw what would you need to show every case to show it's valid. In an exam, if it wanted you to show that it's valid, you'd probably just want to do a proof, like something like that, and then just show what steps you can take. Because if you can prove it with natural deduction, that's how you'd prove it's valid. Because it's provable, and by soundness, it would also be valid. So yeah. Okay, let's talk through this. So, writing this out as a parse tree, it implies, that should not be an arrow, implies, A implies, or, and, so that would be an and, that would be an or, A, not B, A, B. Does that look correct? Okay, let me make this a bit smaller. But yeah, so that would be the parse tree for this expression. So we know implies. We want to tackle the implies first. If phi of B and A or not B, whenever phi of A, sorry. And so if you want to tackle this, if phi of, what line would we put here? What would we turn this into? So we want to turn this into something. How do you break that down? Yeah, if either phi of B and A or phi of A or not B, whenever phi of A. Okay. How could we break this one down? I'm just going to put some brackets around this. But yeah, both, yeah, so, whoops. If either both phi B and phi A, or, and this would be an or, so this would be, or either A or, okay, this is getting a bit messy. If either phi A or phi not B, whenever phi A. I'm just going to add some more brackets here just so we know exactly what's going on. Either phi A or not phi B. That should be around there. If either both phi A and that, or, okay. Yeah, so do we see how we've come from here to here? I don't want to lose anyone on the way. Does that make sense? Okay, cool. And then finally, we'd have something like if either, I'm going to copy this line. The only thing we're sort of going to expand out now is that not B, because that's the only thing that's not an atomic proposition in a phi. So if we move this down, okay. Or and all this would be is or phi b equals false, because then not phi b would be true. And this would then be our mathematical expression, and we can plug in a truth assignment into that to see if it's satisfiable or not satisfiable. Okay, so someone tell me what we could try this with. Just some value of a and b, true and false. Which one should, what should they be? And then let's try and plug it in. False, false. Okay, so a is false, b is false. Let's try that. Okay, if a is false and b is false, okay, so if either both b and a, so both f and f is just f, so if either f or either phi a or phi b is false, so we know phi b is false will be true, so this thing would be true. If either false or true, whenever false. So false or true just becomes true, and this just turns into false implies true. Is that true? Does false imply true? False does in fact imply true. Because we found a valuation where a is true, b is false. So we found a valuation of a and b, or a truth assignment, which makes it satisfiable. Okay, so false implies anything. Yeah, it does. Okay, so we've done that. Now let's try and have a go at, I know it's not quite semantics, but let's just try and prove that it's valid or provable or not. Let's okay, so where would we start if you wanted to prove this? Let's put this at the bottom. First step, scream it out. Implication introduction, good. Okay, what do you do next? Love it. Okay, so we've got something or something. What could we do here? Or introduction. Okay, what side would our or introduction be? Left or right? Right, good. So that means we put the thing on the right here. A or not B. Okay, and then how can we get that? From A, perfect. So that's our assumption. And then we have or introduction left. Boom. Okay, so this is quite a simple proof. This part is quite irrelevant to the thing. Then we can use the intro again on the left. Yeah, perfect. So we've proved that we've said that it's provable, and by soundness, we can prove that it's valid. As in, we can just say that it's valid by soundness. So that's just a brief introduction to some of the semantics, how we can sort of convert between logical expressions into these mathematical statements, which then we can plug in our truth assignments into to see whether it's satisfiable or not. But yeah, checking it's valid and provable, we'd want to sort of use natural deduction proofs there. And then by these two, by soundness and completeness, we can prove that every valid formula is provable and every provable formula is valid. So those two sort of just imply each other. But yeah, that's everything that I really wanted to cover about semantics. I know Hux is going to go into a lot more detail for predicate and how it sort of relates to that specifically. But are there any questions about the semantics of propositional logic? Anything that anyone's unsure about that they want me to go over? I'll take that as... Oh, two people are typing. When might something be valid and not provable? I believe it's to do with the types of language that you use. Like there's some I can't remember, but one of the TAs was working on finding like different types of languages which don't follow this syntactic pattern. So not like propositional or predicate, but other types of languages where there might be some instances where it's valid but not provable, and then that would determine that the language isn't a complete language. So for a language to be complete, it has to sort of meet these two. In process of using phi to prove it's satisfiable, what is it called? That's a good question. I think it's... It might be just extended valuation questions, I'd say. Extended valuation conversions. Truth assignments. The truth assignment refers to the actual values. So like this would be a truth assignment. So I think it's like extended valuation proofs or something along those lines. Yeah. But yeah, we good? Any other questions? Anything else? Okay, if there are any questions, just drop them in general and feel free to @me. I think I'm going to end the session there. Hope that was helpful to you guys. Yeah. I'll see you guys next week in my next session. There's plenty of other fun sessions coming up throughout the rest of the week. Cool. Let me stop the recording.